In this video, we're going to look at how we can use the stack when programming in assembly language. We're going to go back to the example that we looked at in the previous video, in which we were using assembly language to implement something comparable to this Python program, where we have a function that takes a number x and returns x times x minus 1. And that function was being implemented by these 4 lines of our assembly language program. The first 4 lines of the assembly language program implement the global part of the program, where we get an input from the user, store it in a variable x, pass that into the function, get back the result, store that in a variable y, and then print that return value. And we were using register R1 for the input x, we were using register R13 for the result of the function call, and register R14 for the return address. Now, we didn't need the stack in this example because it worked just fine as is. But what I want to point out here is that if we were to add this line to the global part of the program, in which we want to take the result of the function foo, which is in the variable y, and add the original input from the user to it, and have that be the value that we ultimately print. How would we do that in assembly? Well, it might seem that we could just add this line here, and notice it's taking the return value, which is in R13, and it's adding what's in R1, and then that result is stored back in R13, which is what we ultimately write. But this doesn't actually work, and the reason is R1 was changed down in the function when we added -1 to it. And so we don't have the original input in R1 anymore. We actually have 1 less than the original input. And the problem here is that there's only one set of registers, and they're shared by all lines of our assembly program. And so that's why we need the stack. And so what we're going to do is designate a portion of RAM to be the stack. So if you recall, the assembly language program is at the beginning of RAM, starting at memory address 0. And so we're going to go below that, we're going to go further down into RAM, and just say that some range of memory addresses will be set aside for the stack. So here I'm saying let the stack start at memory address 100. And let's assume that we're running a program, this is a different program, in which we're using both register R1 and register R2. So the general idea here is before you make a function call, you want to store on the stack any register values that the function may end up overwriting, may end up changing. So let's assume in this case that we think that it might change both R1 and R2. So what we're going to do is put those in the stack, so the value of R1 will get stored in memory address 100, the value of R2 will get stored in memory address 101. We then make the function call and let it do whatever it wants to the registers. So let's assume that it ends up changing R1 to 7 and R2 to 8. That's not a problem because when we get back from the function, we can load the values from the stack back into the registers, the values that used to be there. And it turns out you do that in the reverse order. So in this case, the 5 will get read back into R2, restoring the old value of R2, and the 3 will get loaded back from memory address 100 into R1, restoring its original value. Now, in order for this to work, we need to use one of our registers as what is called the stack pointer. And we're always going to use register R15 for that purpose. And what that does is it stores the memory address where the next value should be stored on the stack. In this case, we have 100 in the stack pointer register, and so that indicates that the next value should go at memory address 100. And we're going to have to be careful to update the stack pointer either before or after each time that we store something in the stack or load it back from the stack. So for example, after storing the 3 in memory location 100, we're going to increase the stack pointer to be 101 so that the next value to be stored will go there. So let's revise our program to use the stack and fix the problems we were having earlier. So first of all, we need to make room for some instructions before the function call and one instruction after. And so let's renumber things here. You can see the function now begins on line 8, so I'm also updating the call instruction here to make it jump down to 8. So here's what we need to do. At the very least, we need to initialize the stack pointer, and here I'm initializing it to be 100. Then, before making the function call, we want to store the value of R1 on the stack. To do so, we use an instruction called loadr. It takes two arguments, the register whose value we want to store, and the stack pointer. And the important thing to realize here is we're not storing the value of R1 in R15. We're storing it in the memory address that is found in R15, which in this case is memory address 100, which is where our stack begins. Then, after getting back from the function call, we're going to load back the original value of R1 from the stack. To do so, you use an instruction called loadr. It also takes two arguments, the register that you want to load the value back into and the stack pointer. And here again, we're not loading from R15, we're loading from the memory address found in R15, which is the memory address of the stack. And so here we're going to be taking the value in memory address 100 and putting it back into R1. So let's trace through our fixed program and see how it works. So we start by reading the user's input, which we assume here is 5, into R1. We then initialize the stack pointer, R15, to be 100 using a setN instruction. And I'm going to show where the stack pointer is pointing using this little arrow. So you can see that the stack pointer, because there's 100 here, is essentially pointing to this part of RAM. And so that's where the stack is going to go. Then we go ahead and store the value of R1 in memory address 100 using loadr. And why is it memory address 100? Because that's what's in the stack pointer. So that 5 gets copied into memory address 100. It's now been stored on the stack. We can then safely make the function call, and as we saw in the last video, that ends up storing the return address, the address of the following instruction, which in this case is 4, in the specified register, which in this case is R14. We then jump to the beginning of the function, which is on line 8. We do the same things we did before, and notice we're changing R1 with this addN instruction, but that's okay because we're going to be able to get the old value back later. We then do the multiplication to get 20 for R13, and then we jump back to the address in R14, which brings us to line 4. And here's where we're going to load things back from the stack. So that loadr instruction says take what's in the memory address that's in the stack pointer. So because the stack pointer is still 100, we're going to go to memory address 100 and take the value there and load it back into R1. So we have successfully restored its original value, and so now when I add it to R13, I'm going to get the correct final value, which I can then write and halt the program. You'll notice that in this case we never needed to update the stack pointer because we knew we were only going to store a single value. But if you had more than one value to store, you would have to update the stack pointer appropriately, and we'll see that in lecture.